Hi everyone, this is Yongfang, a PhD student from Huazhong University of Science and Technology, Wuhan, China. Today, I present our recent work, namely towards cross-modal forgery detection and localization on live surveillance videos. This is joint work by Xiang Li, Wei Wang, Tao Zhang, and Chen Zhang. Okay, let's get started. With the increasing needs of safety and security in our daily life, video surveillance systems have been widely deployed in various environments such as jewelry shops for customer monitoring, banks for crime prevention, warehouse and factories. In such a system, a surveillance camera monitors a target area and transmits live video streams to a central server for remote monitoring. However, as their prominence rapidly grew in the physical world, these systems inevitably become attractive attack surface in the cybersecurity space. In recent studies have demonstrated that the attackers can sneak into them by exploiting vulnerabilities of the camera or connection cable, and then temper the authentic video streams, which makes that stealing is no longer believing. After sneaking into the surveillance system, the attacker can further trigger two kinds of video forgery attacks, that is, inter-frame attacks and intra-frame attacks. To conceal in inter-frame attacks, the attackers replace the live video frames with previously recorded frames. For instance, the authentic frames containing a walking person can be replaced with frames without any foreground objects. In intra-frame attacks, the attacker removes or adds some human objects in the transmitted frames. As shown in the figures below, the trace of one person can be erased by the attacker while that of another person remains unchanged. Existing solutions to detect such attacks can be mainly divided into two categories, that is, video-only based approaches and RF signal-aided approach. The first category exploits various statistic features of video clips and enable detecting tempered frames and further localizing forged regions in them. Since these approaches rely on spatial-temporal analysis of the whole video clip, they are usually used for post-event analysis and ill-suited for real-time attack detection. The second approach employs handcrafted event-level frequency and timing features from time series Wi-Fi and camera signals to detect replayed video sequences. However, it cannot realize fine-grained forgery localization on each video frame and has a long response time up to tens of seconds. Hence, none of the existing approaches simultaneously satisfy real-time and fine-grained requirements of forgery detection and localization. Under the looming threat of video forgery attacks, it is highly desired for a surveillance system to quickly allow ongoing cyber attacks and seamlessly track potential intruders. Therefore, we ask a question that how to perform real-time and fine-grained forgery detection and localization in video surveillance systems. To deal with this problem, we present SecurePose, a novel system that exploits the pervasive coexistence of surveillance cameras and Wi-Fi devices to detect video forgery attacks. Specifically, it enables real-time forgery detection and it facilitates fine-grained forgery localization. To develop our system, the key insight is that similar to surveillance cameras, Wi-Fi devices can also probe human objects. Nowadays, many areas under surveillance cameras are also covered by Wi-Fi hotspots to provide us wireless connectivity. In such areas, not only visible lights but also Wi-Fi signals interact with human bodies. Specifically, according to Wi-Fi CSI motion model, the CSI at time t, frequency f, and antenna I can be expressed in the sum of static and dynamic channel frequency responses. Since human body acts as reflectors in the Wi-Fi frequency range, the movements of the human body can be reflected in CSI measurements. For coexisting camera and Wi-Fi devices, their signals convey common human semantic information. If forgery attacks are launched on video frames, such cross-modal information correspondence will be decoupled, which can be exploited for timely forgery detection and accurate forgery localization. To realize above idea, we need to address two challenges. The first one is how to effectively distinguish human semantic information from CSI measurements. Specifically, when CSI measurements has much fewer elements than one image. For example, one CSI measurement generally has 270 elements, while one 48p image has about 300 key elements. Thus, the mapping from one CSI to one image is a highly ill-posed problem. To address this challenge, we first need to relieve the above ill-posed problem, considering that one Wi-Fi device usually have a much higher sampling rate than that of a camera. We correspond multiple CSI measurements to one video frame for increasing the number of input elements. Then, we formulate feature extraction as human pose estimation and estimate joint heat map and part affinity fields, which are retrievable from both images and CSI measurements. Next, we design an effective cross-modal learning framework. Specifically, we use the will-learn open pose to transfer one video frame to PF and JHMM features. Then, we build a customized cross-modal network, namely CSI2-pose network, to estimate PF and JHMM tensors from CSI measurements. Moreover, to make sure that CSI2-pose network has useful outputs, we train it with the supervision of the open pose network via a cross-modal training scheme. The second challenge is how to efficiently detect and localize forgery traces in each video frame. Since we have visual and wireless JHM and PF tensors extracted from concurrent video and Wi-Fi signals, a straightforward way is to assign detected key points for human instance with full body poses respectively and perform forgery detection while calculating pose similarity in a person-wise manner. However, such approach is cumbersome and computationally inefficient. To attack this challenge, we need to preserve sufficient information about forgery traces and remove redundant one. For these papers, we calculated the difference between visual and wireless tensors. The rationale behind the difference operation is that with efficient feature extraction by our cross-modal learning framework, Wi-Fi and wireless JHM tensors would be very similar, making the difference tensor having a lot of near zero difference in the authentic area. In contrast, when video forgery attacks appear, body poses in the video frame is modified and the visual JHM tensor will change accordingly, which results in large difference in the tempered region. Then, we detected and localize attacks with modified JHM and PF features. Specifically, we input the JHM feature tensor into a simple detection network to accurately determine whether forgery attacks exist or not. Once attacks are detected, we combine visual and wireless feature PF tensors into a PF sound tensor and leverage it with candidate key points to localize abnormal objects only in the tempered regions. The system flow of secure pose is given in this slide. It takes concurrent camera and Wi-Fi signals as input. After that, it first performs multi-modal signal pre-processing to synchronize two modalities. Then, it estimates JHM and PF tensors from video and CSI signals, respectively. Finally, it facilitates forgery detection and localization with combined JHM and PF tensors. Implementation. We implement our system use one Logitech 720p camera and two Internet NICs that are embedded in two NUCs, as shown in the figure. One NUC is used as a transmitter and the other as a receiver. For a good field of view, we mount the camera with a height of 2 meters and place it on the receiver side. During data collection, we ask different numbers of volunteers to perform daily activities such as walking, sitting, waving hands under the camera's FOV. First, we report the detection performance in terms of TP rate, FP rate, and accuracy. As the table shows, our system achieves comparable performance under inter-frame and intra-frame attacks. The overall detection accuracy is 95.1%. In particular, they can successfully detect 94.9% of tampered video frames and correctly recognize 95.3% of authentic frames. Then we show its ROC curve. As the figure shows, the ROC curve closely follows the left hand and top borders of the ROC space and produce a high AUROC of 9.983, which is close to the ideal case. The above results show that our system achieves good detection performance under inter-frame and intra-frame attacks. Second, we present the localization performance of our system. We use percentage of correct key points as our metric, which is defined as a ratio that normalizes the distance from prediction SJP to the ground truth YJP of J's key point or P% is less than the threshold, though, as the figure shows, the localization performance of abnormal objects' key points yields high PCKs at low normalized distance errors. Moreover, it also can be observed that our system always has a higher mean PCK under intra-frame attacks in terms of different normalized distance errors. The reason is that compared with inter-frame attacks, intra-frame attacks has a smaller modification on GHM and PF tensors, which yields a higher accuracy on key points localization and association for abnormal objects. Additionally, we showcase the outputs of forgery traces under inter-frame and intra-frame attacks. In the inter-frame attacks, we replace a authentic frame that has 3 persons with a blank background. In this case, the absence of 3 persons is successfully detected by our system, and then their associated body key points are accurate estimates. In the intra-frame attacks, 1 of 2 persons is erased from the original frame. In this case, our system correctly localizes such forgeries and plots the body pose of the erased person. The above results suggest the effectiveness of secret pose in localizing different forgery attacks in each video frame. To conclude, we show that the coexisting camera and Wi-Fi signals share information correspondence, enabling cross-modal detecting localizing video forgery attacks. We propose a secure pose, a novel cross-modal forgery detection and localization system that can discover forgery traces in live surveillance videos. We implement a secure pose using a commercial Logitech camera and 2 Internet NICs and conduct extensive experiments in real-world environments. Thank you for your listening. Any questions or comments will be appreciated.